And now it's time to welcome Edoardo to talk about Rust. And I will. So Edoardo is bringing Rust and CHERI together in practice. With a background in compilers, he has been working since day one on CHERIoT and Rust integration, showing how compile time and runtime guarantees reinforce each other. So we have to do a bit of setup here. Okay, should be good. Yes.
Thank you. Okay, hi. So we all know and love CHERI. We know its value, we know what it does, and some consider Rust to be a solution to exactly the same problems. And the two technologies are often described as mutually exclusive, as forces pull in opposite directions to solve exactly the same underlying issues. The story is often that you just need to choose one, and if you use CHERI, you don't need Rust, and if you use Rust, you don't need CHERI. And my objective today is to explain why that's not the case. And in order to build safe and reliable applications, your best chance today is to use both. Right, and CHERI, we know it gives you special safety. These three snippets, they will all deterministically trap on any CHERI platform. And the processor itself will raise a trap, and you will be able to handle it. And CHERI also gives you temporal safety. Specifically, this use after free will trap on CHERIoT. It will deterministically raise a trap, and the RTOS will give you the facilities to handle the trap and continue execution of your program is in a known state. Rust probably doesn't need an introduction either. We all have heard of it at least once. And perhaps its most common or known characteristic is the emphasis it puts on memory safety. At its core, originally, Rust tried very hard not to invent anything new, but to build on well-studied, well-understood results from research on programming languages to build an industrial-strength language that is as close to the machine as a language like C is, gives you a type system that is as expressive as those commonly found in functional programming languages such as Haskell, and most importantly, using memory safety without making execution too slow, right? So Rust, again, also gives you special safety, and all these snippets will, the specific ones will also just not compile if you insert the correct lints, because of course a compiler can infer that you're trying to access something out of its bounds. So cargo, which invokes Rust, the Rust compiler, will just error out. And perhaps most importantly, Rust also gives you temporal safety, and Rust employs a borrow checker to track lifetimes of the objects in your programs so that you don't do accesses such as this one, again, use after free, and Rust will just won't compile your program. So the question now is, why? Why exactly are we trying to make Rust work on CHERIoT? And there are many different reasons. The short version, you can see here in this table, we have all the positive values of these two technologies. The short version is that, well, you get all of this, of course, but the mechanism, the sense, is that Rust is useful to build new applications and to make safe fragments of your code, safe with all the checks that the compiler enforces for you. But you're again on your own when you get to interact with other libraries written in C, for example, or when you turn off the safe, you enter the unsafe fragment parts of Rust, because Rust also gives programmers the ability to, a sort of an escape hatch, an ability to say, I don't want these checks, turn them off, I trust my code, I know what I'm doing, just don't do all your checks. And this is often necessary when you either need to interact with, say, a kernel written in C, or a library that your vendor gives you, or you just trust your code again, and you just don't want to pay the overhead at runtime to do some specific operations. And I have some demos here to show you in practice what this means. I have here, in this example, I declare two vectors, and I want to use the items from the second vector to access values from the first one. Here, of course, the error is obvious, but the point is that when we enter the unsafe code and we use this function get unchecked, which turns off the dynamic checks that Rust inserts for you, you're on your own in the sense that, as the documentation says, calling this function with indices out of bounds is undefined behavior, even if the resulting reference is not used, right? So let's see if the demos work. Let's do one-handed demo. So. Sorry? Yeah, no, it's fine, it's fine. I just need to push a button. Yeah, thank you. All right, I'll put this one here. Turn it off, I guess. All right, so again, just pushing a button, but if I execute this on my host, on my laptop, I get 1, right? Because when I get to the second index, when I try to access the second value from the indices vector, I just read memory from a vector, a part of memory that happens to be right beside the first vector, but then my program is in undefined state. Of course, if I execute the same thing, this is a CHERIoT simulator running this Rust program, I get, of course, a bounds violation, right? And the second example I wanted to show you is this, where we have, okay, you can see the pointer. We have a C function, which just takes a sequence of bytes and verifies some properties of this input and returns the valid length of the string it computed. For some reason, say, again, a vendor just gives us this library. We can't rewrite it in Rust for, we don't want to bear the costs of rewriting it, or we don't have the time. And so we just call the C function from C. Again, it's in an unsafe block because interfacing with non-Rust languages is intrinsically unsafe. And we just get the input from the user, a string, and we pass a pointer to the string to the C function. Now, the error here might not be immediately clear. The problem is that in C, strings are normally non-terminated, in this, meaning that they have a final byte, a 0 byte, which indicates the end of the string. And that's the mechanism that strlen function uses to get the length of the string. So it's not the same in Rust. Strings are not terminated. Strings are represented as a struct with a sequence of bytes, yes, but it also contains the length of the array, of the vector. And so when we do this, when we call this C function, C continues to read the memory of the string, but won't necessarily find a 0 until it comes up in memory, but it's undefined, right? And when we get back to Rust and we rebuild the string, getting the length that this function computed, and we rebuild the string, supposedly the correct string, our program will be in an undefined state. So let's see how it looks. I have here simulating the input from the user to strings, and what we'll see when we run this, right, that C function, that C bit, didn't understand, couldn't figure out that the length of the string, that the string ended, and so thought that the length of the string spanned the two strings. So now our program is in an undefined state. And even more wrong is we think that this is the correct string, right? We don't get any idea that something went wrong. So when doing this, the same thing, running the same program in CHERIoT, we get an issue, right? We get a trap. And furthermore, we can also, as you can see here, I'm printing this line. We can also handle, right here, we're just gracefully exiting, not doing anything else, but we can also continue execution and deal with the error in a deterministic and correct way. And let's get back to the slides. There is another important thing we need to talk about, what CHERI gives you, which is strong isolation of untrusted code, also known as compartmentalization. Compartmentalization is a mechanism to allow safe isolation together with shareability. You can think of a compartment as some code with some objects. And for example, here, when compartment C1 passes control to compartment C2 will be able to see only the objects that C1 consciously shared with C2, and furthermore, C2 won't be able to access the stack from C1. Right, so I have an example of this as well in Rust. Say that we have a bit of code that we wrote with Rust. We get a password and username from the user, and for some reason we want to record this access using a third-party crate, which we don't necessarily trust. And so using CHERI, we can put the untrusted crate, the untrusted third-party code in a compartment. And without it, someone can use, this is a supply chain attack, someone can perform a supply chain attack, getting a pointer to the frame of the caller and getting a handle to the password. So let's just look at it on my host machine. If it works. Right? So nice password, right? Alligator1, but we can see it, right? And the kvlog crate is able to do some pointer arithmetic to get a handle to that variable in the stack. If you execute the same thing with proper compartments on CHERIoT, we just get a violation from the RTOS telling you that you're not supposed to see the frame address and then do maths on it. Right. And how are we doing this? Well, DSDB funded us last year to work on this. And the first step of our work was to adapt previous work done on Morella to readapt it to the latest Rust release. Then we added the CHERIoT target and the CHERI intrinsics, and we made parts of Rust standard library work on it. And right now we are at this stage, testing these parts. After this, we'll have to add CHERIoT-specific front-end attributes so that you're able to specify calling conventions, MMIO, and shared objects. Integrate with the rest of the CHERIoT platform, that is, put it in CI with the RTOS and things like that. And finally, we want also to enforce Rust properties at compartment or FFI boundaries. So meaning if the Rust type system says that a pointer is constant, you lose that information when you get to assembly, right? But with CHERI, you can actually enforce that. And so that's what we will try to do. Regarding the change to the compiler, the main difficulty was convincing the compiler that pointers and what you can represent with pointer, what you can put in pointers, such as addresses, and how you store pointers are not the same, right? They're two different things. One thing is how many bits it takes to store a pointer and how many bits of data I can put in this representation. Other changes were to convince the compiler not to transmute, because transmuting between two differently sized types result in poison, so it will just trap at runtime. So we had to instruct the compiler that you can just transmute between, you can consider usize and a pointer type as the same thing. And right now, some numbers, these are what we are working on, doing more tests. We have part of the test suite passing 60% of code general VM tests. This test just compile Rust programs and compare with a known LLVM IR. They compare to verify that Rust emits what it expects. And so this don't run is just checking that the text produced, the IR produced, is correct. Other tests are those that test the core libraries, which actually run. And here we see a 57% of these pass and 43 need investigation. And of course, just making it work is not the whole thing. It's only part of the story. And we also need to have a plan for the future. And what we'd really like to do is to make our work part of the proper Rust and make it, upstream it, and so that we're also able to maintain it in the future. But of course, this is not necessarily a specifically technical task. It also requires lots of social skills. Final question is where? Of course, SCI recently produced a dev board with a CNI. Other than that, you can try out Rust on the Sonata board. Here you can see the embedded graphics crate working on Sonata. Otherwise, we have the dev container with some simulators and Clang and RSC. And yeah, all the work is open source, lives in the CHERIoT repository. You can scan the QR code to get a link to it. And that's it. Thank you.
Okay, I should have mentioned that you are also the co-lead of the Rust and CHERI working group in the CHERI Alliance. So thank you for that. Question here.
Thank you for your talk. I mean, you talked a bit about unsafe Rust, when you're calling C functions and so on. But isn't the problem even worse? I mean, my understanding is even in the standard Rust library, a lot of the string functions are safe abstractions, but over unsafe code. And so, I mean, is the implication actually you just can't write a lot of useful algorithms in safe Rust?
Yeah, it's not easy to do. There are some specific data structures which are hard to represent in Rust. And Rust itself is not written entirely in safe Rust, right? There are some unsafe bits, and I guess it's more of an engineering question. Is someone able to write it in safe Rust? But even then, even if your entire software stack is written in safe Rust, does it contain bugs? The compiler itself, are there soundness holes which can be used to slip through the cracks of safety and introduce things that are unsafe but are not marked as such? So yeah, there's definitely is, I guess, it's a problem.
The Rust community definitely needs CHERI.
Yeah, exactly.
Other questions? Okay. So thank you again.
Thank you.